Question 2, we're given a vector field big F, defined as you can see here. We let C be a curve as described as a parabola given by this equation. A is greater than 0 and the parabola goes from 1, 0 to 2a. And our job is to compute this integral. Okay, so question 2a, we begin by observing that we have a parameterization. So we parameterize C as gt like this. So it's a pretty standard parameterization, and t goes from 1 to 2. Okay. Then our integral, or rather our line integral, looks like this. Gt g prime t dt. And that goes from 1 to 2. So this is just a 1, 2, open bracket, a t minus 1 square, divide by t square plus a square t minus 1 to the 4, comma, minus t close bracket, dot. And now we take the derivative of this and that. So this is just going to be 1 comma 2a t minus 1 dt. And just as an aside, this expression here, that's just y over x squared plus y squared with the parameterization subbed in. This expression is minus x over x squared plus y squared. All I've done so far is just sub into parameterization. So now let's simplify that dot product. 1, 2, so I have a denominator. So the numerator is a t minus 1 squared times 1 minus t times 2a times t minus 1 divide t squared plus a squared t minus 1 to the 4 dt. And now we simplify. So this is a times t squared minus 2t plus 1 minus a, and then 2t will multiply in, so that's 2t squared minus 2t. And the denominator is the same. And then from here, I'll factor out the minus a. So this becomes minus t squared plus 2t minus 1 plus 2t squared minus 2t. And the denominator is the same. And quite obviously, you could cancel out this term with this term, and these two terms can simplify. So that's equal to minus a integral t squared minus 1. And I'm going to, let's see, leave the denominator as it is. So Sorry, I copied it wrong. This should be a t square. There we go. I thought something felt weird. So the denominator will stay the same. And I have a dt. So it's really just an integral of one variable at this point. Divide everything by t squared. So this becomes a 1. Okay, and then what can we do from there? From there, I'll re-express the denominator as t inverse t minus 1 square t inverse times t minus 1 square. So it might not be clear as to why I made that re-expression, but you'll see why soon. So now I'd like to solve this. I'd like to make a substitution. We let ut be equal to this. And if you're to simplify it, that's a square. And if we're to simplify it, we have this. That's t minus 2 plus t inverse. So if we took that and we take the derivative, so du dt, that's just 1 minus t minus 2, t to the power minus 2, which you could kind of see up there. Okay. So if t is equal to 1, then u is equal to 0, and if t is equal to 2, then u is equal to 1/2. So compared to this integral up here, we now put in the substitutions. What do we get? We get this. So the integral from before is now equal to 0, 1/2. We just have a one du on the top, and on the bottom it's going to be 1 plus a square u square. Yeah. So this simplifies off to 1 over 1 plus a square u squared du. And now this is really straightforward. This is now just arctan, if you could see it. Oh, and the minus a from before too, and there's a minus a. So this is equal to negative arctan, or tan inverse, au. U goes from 0 to 1/2. So that's just negative tan arctan. And the second expression is just 0. That's a over 2. And that's it for question 2. So truthfully, in all the work that was done, once you realize that you have to parameterize c, and we have this line integral, and you simplify it, once we hit this step, then it's just an integral of one variable. And it's just the standard integration techniques from there. Just keep playing with it until you have what you want. So the final answer itself is negative arctan of a over 2, but all the real work was done from before. So that's it for question 2.